Hello there, I am Professor Gadgil, meeting you for the first time for this course in Masters in Structural Engineering. I first of all welcome you all for opting to go for higher education in structural engineering. After your graduation, you had several options, but of various options, you have selected one to go for further studies. When you have studied or you were studying for your bachelor's, you had studied several subjects, and in each semester, now when you look back, you will realize that there was one subject pertaining to this branch of civil engineering, structural engineering, in terms of either engineering mechanics, strength of materials, structural analysis, structural design, dynamics of structures, earthquake engineering, and so on and so forth. After completing your graduation, now in civil engineering itself is a branch of engineering. Now you have taken further specialization as structural engineer, and now you are studying one small part of civil engineering, which is structural engineering. When you study structural engineering now at your masters, you will realize that it is a vast branch with innumerable applications in different fields. So now it will not remain a small part of civil engineering, but it in itself will be a full-fledged branch of civil engineering. You have studied several subjects in your earlier courses. Now you will be studying maybe 5 or 6 courses. If you see the syllabus, you have several subjects in structural engineering now: computational methods, the continuum mechanics with which I will be concerned with. Then you have experimental methods in structural engineering. Then advanced geotechnical engineering. Then you will have 2 electives, elective 1, elective 2, and there are some laboratories for experimental methods and numerical methods. As far as the electives are concerned, you have in all 3 electives, out of which you have to take 2. The nonlinear analysis is one, mechanics of composite materials is another, and repairs and rehabilitation is the next. If you see the various subjects which you will be studying in semester 1, one is your computational methods. If you look back to what you have studied in various subjects in structural engineering, or for that matter, some subjects in civil engineering also, you must be remembering that many of the problems are finally converted into mathematical equations, either differential equations or algebraic equations, integral equations, and so on and so forth. And you have to solve those equations to finally get the answer to a problem in structural engineering. So you have to first of all formulate a problem in terms of equations and then see which methods are available. And one subject which now you will be studying in detail is computational methods, where you will be studying various methods of solving those equations which we come across in structural engineering. If you see experimental methods, another subject which you will be studying, you must realize now that you are studying the theories, but civil engineering, or for that matter any branch of engineering, is not just a theory. It has to be put into practice. So while deriving the theories, writing down equations, you make several assumptions. With those assumptions in mind, you formulate the problem, solve the problem, and you get some answer to the problem. And now, based on those answers, you try to actually deal with the real structures. So you predict something on paper, you construct the structure for that matter in civil engineering, and then see whether your prediction is true in real life structure. If it so happens that your prediction was one thing and what you observe is quite different, then either you must modify your theories or modify the way you have built the structure. But there should be a reasonable agreement between what you predict and what you actually observe. So we have the experimental methods to verify precisely that you have predicted something. You measure and confirm whether your prediction is true or not. Then you have advanced geotechnical engineering, wherein you will be studying one branch of civil engineering in detail, the geotechnical engineering, because finally most of the civil engineering structures rest on soil. The behavior of the entire structure above ground is therefore to be, you can say, the basis of that, its behavior, or you can say its performance will be tremendously affected by the geotechnical aspects of foundation. So there are many complexities involved in predicting the behavior of soil below, and you will be studying some part of that in this particular course. If you see the electives, then you will see that in the electives you have nonlinear analysis, where you will be studying the behavior of the structure when the elastic limit is crossed in terms of material nonlinearity, or when you have got geometrical nonlinearity where very large deformations occur in the structure and the prediction of the behavior of the structure is not linear. So you will be studying one elective pertaining to that. Then you have mechanics of composite materials. If you remember the way you have studied various subjects, then you always made an assumption that your material is homogeneous and isotropic, which means everywhere it's the same properties. But many civil engineering materials you will see involve composite actions. You have reinforced concrete involving concrete as one material and steel as another. Likewise, there are many more complex materials than concrete, and to use these materials to understand the behavior of structures made up of those materials, you will be studying this particular subject, mechanics of composite materials. Then you have the repairs and rehabilitation of structures, which is also one of the upcoming branches in civil engineering, because as the structure becomes older and older, you have two options to use the structure. One is to pull down and build a new one. Other is to repair and rehabilitate the structure and bring it to a reasonable level for its intended use. So there are many technologies available for the second option, repairs and rehabilitation. You will be studying that as the third elective. Of course, you have to select two of the three electives and then see how best you can understand those principles involved in those subjects. And now we will be concerned with the continuum solid mechanics. You have studied in the earlier courses, you remember, strength of materials, where you have studied, if you remember, the theory of bending, where you have calculated the stresses arising out of bending moment. You have seen how the shear forces are converted into shear stresses. You have also seen the principal stresses, the planes on which they act, and so on. You have also studied further, you remember, the conversion of torsional moment into torsional stress, and so on and so on. The subject that you have studied earlier, strength of materials, is many times called as elementary strength of materials because several assumptions are made in converting those forces, the axial force, the bending moment, the shear force, and so on into the respective stresses. But many situations arise where we come across limitations of those theories, and then we have to search for a better solution than that is given by strength of materials. You have also studied in strength of materials the problem of calculating deflections, primarily due to the bending moment in case of beams and frames, and due to axial forces for the trusses. But again, as the deflection is calculated due to bending moment, it is based on the theory of bending. So whatever the limitation that you had for the theory of bending, same would be applicable to the deflections also. So if you want to refine your understanding and narrow the gap between the predicted behavior and the observed behavior, then we have to go on reducing the number of assumptions, go for realistic structure, its idealization, a refined idealization, and then predict the behavior, which we say brings you closer to the reality. If you see the primary objective of structural engineering, for that matter, as a structural engineer, when you want to master it, you must realize that as a structural system, when your objective is understood properly, for example, if you consider the primary objective of structural engineering, then you will see that in structural engineering we have first of all a structural system, a structure for that matter. Secondly, it has to carry some loads, and thirdly, we say that the structure must be so designed, so analyzed, so planned, so constructed that it carries the load applied on it safely and efficiently. So first of all, we have a structural system. Now what is a structural system? So we say that if you ask a common man what a structure is, then common man has got some vague idea as to what he means by structures. So he will say, oh, there might be buildings, or there are bridges, or there are fluid containing tanks like water tanks, oil tanks, and so on. Or there are many times retaining walls in hilly areas where you have to retain the earth which is otherwise going to slip. Then you have the dams where water is retained on one side, or you have the aircraft structure which floats in air, carries the weight from one place to other place. Then you have the ship which floats on water, again carries weight from one place to other place. Then you have the automobiles which move on the road surface, but again they carry some loads. Then you have the tunnels for passage of roads or railways or pipelines. Then you have the jetties which are there for berthing of ships on the port and harbor. Then you have the cranes for lifting material. These days many construction sites you will see those tower cranes are erected for transport of material from ground to the required level. Then you have the balloons which many times were used, or even for entertainment purpose people use it for taking the object up the sky, transporting it from one place to other place, and so on and so on. So from the functional point of view, a common man understands structures. But as an engineer, if you want to again put down your understanding, then you will see that for an engineer, this type of functional description is not proper. For an engineer, he will say, oh, it might be a beam as a structure, or you might have a column as a part of structure, or you might have an arch, or you might have a cable, or you might have a truss planes or space truss. You might have a frame which may be either a plane frame or a space frame. You will have a floor grid system. In many buildings you will see the floor grids are provided on which you are putting some loads. Then you have the floor slabs. While in floor grid you have got beams and slab construction, while the slab is a two-dimensional medium. Then you have the shells, which are three-dimensional structures, many times used for roof of different types. Then you have the folded plates, many times they are used as roof. Then you have the 3D solids, used foundation blocks. Then you have the plane stress problem, which we will be studying in detail, the plane strain problem, and so on and so on. So you will see that the understanding of common man as a functional description for structures and this proper, you can say, itemization of different components of structures is what an engineer tries to understand. In that also, if you see various types of descriptions which an engineer gives to structure, if you try to see that if the loads are applied on the structure, so we say that we have a structure made up of several you can say components. For that matter, therefore, we say that if you properly define the structure, then we say it is structure is an assemblage of members suitably connected to each other and supported so that it carries the load coming on it safely to the support or foundation. Thus, the basic building block of any structure is a member or an element which may be 1, 2 or 3 dimensional. So we say that structure basically is an assemblage of members. So now we say that if that is the case, then what are the basic elements or the building blocks of the structure? So we have truss element, the members of the truss, which carry primarily axial force, maybe tension or compression. Then you have the beam element, which carries primarily the shear force and the bending moment. Then you have the 2 or 3 dimensional frame element, which carries axial force, shear force, bending moment, and so on. Then you have the slab, the 2-dimensional medium as we say, which has got bending moment as internal force, the torsional moment, and the shear force. We have the plane stress element, which we will be studying in detail in the present coursework, wherein we have the stresses in it, sigma x, sigma y, and tau x. You have the plane strain element in plane stresses and out of plane stresses, developing sigma x, sigma y, sigma z, and tau xy. We will be seeing the detailed description of these stresses shortly. Then we have the membrane element, like a balloon or a shell, where it carries primarily the in-plane stresses sigma x and sigma y. Then we have the shell element, a concrete shell for that matter, which carries membrane forces Nx, Ny, Nxy, the shear and the bending Qx, Qy, Mx, My, and Mxy, the torsional moment. And you have the solid element, which carries normal stresses sigma x, sigma y, sigma z, and the shear stresses tau xy, tau yz, and tau zx. So we see that as a building block. Now we have these structural elements. They go assemble into a structure, and then you have a structure carrying loads. So we say that the basic building block that we have made up of several elements, they have to carry the loads. So let us see what kind of loads we anticipate on the structure. So we say that for a structure, if it has to carry loads, we classify the loads in a broad manner. So we have the gravity loads, which may be dead load, lie load, floor finish, and so on and so forth. Then we have the inertia forces arising due to seismic effect, due to vibrations of structures and so on. Then we have the wind load applied externally on the structure. Many times you have to deal with thermal loads where there is change of temperature that gives rise to a lot of internal forces developed in the structure. Then we have the wave forces where offshore structures are subjected to such types of forces. Then we have the electromagnetic forces developed in many of the electrical engineering equipments. We have real life structures subjected to many times blast loads, impact loads, and so on and so forth. So there are many structures which are designed for these kinds of situations. As far as any structure is concerned, when it rests on foundation and if that foundation itself settles due to whatever the reason, then that gives rise to many times huge internal forces in the structure, and we have to design the structure if you know beforehand how much will be the settlement. You have to design the structure for catering for those settlements. Many times the manufacturing of the structure itself or its materials develop some internal forces, and you have to cater for those forces when the entire structure is built. You have the buoyancy forces. Many times even the underground structures like the basements and so on, they have to be designed for buoyancy of the water coming from below. When you have the creep and shrinkage, many times it's a primary you can say phenomenon in concrete where due to sustained load, that is load applied over a long period of time, concrete undergoes progressive deformation. So there is one instantaneous response and there is a response which increases over a period of time, and a shrinkage of concrete which many times lead to very severe internal forces and so on and so on. So we see that we have to design our structure for all these loads and maybe many more loads later on depending upon specific application that you deal with. So we have the structure and an assemblage of members to carry these loads and to carry these loads safely. As far as the loads are concerned, that is many times an external phenomenon, but the structure develops as a resistance internal stresses due to these external loads. So we say that the primary objective of any structure therefore is the external loads, the structure resists internal forces while resisting the external loads. And now let us see what internal forces a structure develops. So though there might be various types of loads which we have listed, for any structure for that matter, when you have got these building blocks, truss, beam, frame and so on and so forth, we see that only 4 types of internal forces are developed in the members. There might be axial force, which is either tensile or compressive. There might be shear force, there might be bending moment, and there might be torsional moment. Either one, two, or all of them are developed in the structures. So we see that no matter what structure you are considering, no matter what loads are considered, innumerable structures, innumerable loads, but internal forces are only of 4 types: the axial force, the shear force, the bending moment, and the torsion. If you go one step forward and see that okay, you have got forces, but what stresses are developed? So you must distinguish between a force and a stress. Force is a gross quantity, while stress we say that it has to deal with something which is on a different level. So you have the member carrying so much of force, say kilonewton, tons, pounds, whatever it is, or kgs. While you have to many times consider another quantity called stress, which is nothing but force per unit area. So for any structure, once you say there are four types of forces, then we see that what types of stresses are developed. Then we see that you have got only three types of stresses. The normal stress, which may be tensile, the normal stress, which may be compressive. So we have only normal stresses, one type, and the other is the shear stress. A normal stress is perpendicular to the plane that you are considering an elemental area, while shear stress is in the plane itself. So we see that we have started with a structural concept, hundreds of types of structures. Then we have several building blocks of the structures. Then we have four types of internal forces developed in the structure, and basically only two types of stresses, but we have further classified that into three because the behavior is sometimes different: normal stress compressive, normal stress tensile, and the shear stress. Now we say that we have a structure which is to be made out of materials. So various types of materials we deal with, and now we say that as far as the materials are concerned, we have different types of materials. We have the natural materials, if you try to classify that, the man-made materials, the combination materials, we have the structural materials, sometimes you have the aesthetics material, or you have the functional materials, and so on and so on. So many different types of materials are being made, they are used. As far as natural materials are concerned, we have listed few, but many more can be added to that. The soil, the stones, the sand, which we can say either crushed stone or natural sand. Then we have the timber, we have natural fibers, which are available in nature, we can say jute or bamboos fibers are available. Then we have the hair, human hair or animal hair. We have the skin, the animal skin many times is used in some applications. We have the bone also used in some applications. The natural material, water or air, and so on and so on. So these are all different materials which go into structures in one way or the other, and you have to deal with them. Well, as far as man-made materials are concerned, we say we have the bricks, we have the concrete, we have the metals, the non-metals, polymers, man-made fibers, and so on and so on. Because metals also you can say they are available in terms of bulk or rods or in terms of fibers. So we say that there are various types of materials available. Now in the olden times, people tried to understand the behavior of simple structures, like the attempt made by Galileo to understand the behavior of beam, in Robert Hooke to understand elasticity, Bernoulli, Euler, and so on, who tried to understand the buckling problem or the bending problem. So these historically, you can say those times were the time when people tried to formulate scientific basis for predicting the behavior of structures, and many theories were developed in those days. You can say that as far as the theories developed in the olden times were concerned, several assumptions were made, governing equations were derived, and behavior of structure was predicted. So we have the elementary strength of materials, wherein you remember we have studied the theory of bending, that is converting the bending moment to bending stress, either tension or compression. Then you had the theory which enabled you to convert shear force into shear stress. Having considered shear stress and the normal stress, then you have the principal stress concept, which will give you the maximum value on some plane. Then you had studied the torsional theory, which enabled you to convert torsional moment into torsional stress or the shear stress. You have also seen methods of calculating deflections. That is all part of elementary strength of material. But when you see real life problems, then you will see that in real life, you have got, for example, if you take the simplest problem of a beam carrying point load, then we say that near the point load, where on a very small area you have put some load, locally you will say that the stresses might be very high. Near the support, you have got a large reaction developed, again leading to very large stresses very close to the support. Similarly, at the joints, where a beam is connected to column or members of the trusses are joined to each other, you will see that at those joints, very complex stresses are developed, and the theory that you have studied, elementary strength of material, is not in a position to address such types of stress. Many times you have got beams which are quite deep. In elementary theory of bending that you have studied, you have made an assumption that plane section before bending remain plane after bending. Now that is generally true only when you have got beam whose depth is reasonably small compared to its span. But many times we deal with beams which are quite deep, and if you want to understand the behavior of deep beam, obviously the theory of bending that you have studied is not going to help you. You need better theory, refined theory, devoid of many of the assumptions made in normal theory of bending. Many times you have to deal with rollers or ball bearings, and if you want to determine the contact stresses between the roller and the surface on which it moves, then you will see that the normal theory that you have studied in strength of materials is not able to address that. Where you have got change of cross section or change of materials in beams and shafts and so on, for whatever reason, again you will see that such changes lead to localized stresses which are quite different than those given by elementary strength of material. And many times you have to deal with semi-infinite or infinite medium. Like for example, if you take a foundation, then you have got a foundation which rests on soil, but that soil is a vast mass. So how the dispersion occurs below the foundation? Now this type of problem cannot be addressed by strength of material. So we see that the complexities of real life structures enable or will force you to go for more refined theories rather than relying on the elementary strength of material theories. You have made assumptions in your earlier courses while analyzing structures that The material that you are going to use is isotropic, which means properties are same in all directions. But in real life, you will always see that it is very difficult to get such material. Many times we deal with orthotropy, which indicate that properties are different in mutually perpendicular directions, like fiber reinforced plastics, where they are very strong in one direction and not so strong in the other direction. While if you take anisotropic or anisotropic material, then you will see that for these materials, the properties are different in different directions. As far as homogeneity is concerned, we will say that for homogeneity, we make an assumption that the properties are same everywhere. But many times we deal with materials which are not homogeneous, like reinforced concrete. So you have got concrete having some property, while steel reinforcement that you have used has got different property. So at a micro level, we will not be able to call concrete as homogeneous, reinforced concrete for that matter. While if you see the simple definition of stress that now you are going to calculate, then you will see that the stress at a point, if you want to work out, then we will see that generally the stresses do not remain constant throughout the body. They are calculated on a small area, and for that small area we just want to know what is the average stress. So you work out the total force on the area, then consider the area on which the force is applied, and then take the average stress as delta P by delta A, which is now we say as the average stress applied on it. Okay. I think we'll take a break for maybe 5 minutes and then continue with our discussion again.